See the boards again, and Ruben is going to talk about the prepared studies that have been performed.
I will present three sets of results. First, we start with sensitivity studies. The objective of this study is to justify the assumptions that we make in the abstract that the in situ soil and the engineered field, which rest on the top of the rock, are negligible for the seismic design of USDWR, Category 1 buildings and equipment. So now we do the site-specific evaluation of soil embedment effects from the active field building and the controlled building design, which are based on models that are embedded in full column soil profiles presented in section 3.71. And now we do comparison of the whole set of results to see what these effects are. First, you look at the transfer function, manufacturer response spectrum, maximum and the forces, and compare them to what we used to be a standard design basis for, and the Unit 3 site-specific design basis as documented in the abstract. Now, so far, we are almost completed with all these runs. We have results for 5 sets of analysis, for control building with bit analysis for all 3 full column profiles, a lower bound, SSM, and upper bound. We finished the runs also for reactor building, lower bound, and upper bound column profile. So what you're going to see as a result is basically based on this run. Now, the next slide, 51, shows the model we use for this analysis. Basically the same as the model we use for the partial column, and we have addition of layers above the rock, and as you can see they're more refined in order to meet the requirements of passive frequency. We have the same modeling approach as we had for the licensing basis of partial column analysis. The model, the profiles represent properties of in situ material, and then all the backfield, engineered backfield, we add it as a part of the structural model as it's shown in this slide. Now, we use based on subsidy requirements that the 1/5 of the wavelength should be the maximum size of the element. We can measure this model to transmit frequencies up to 55 Hz. This is an upper bound source. The next slide shows the profiles itself, and it gives some information regarding the shear column frequencies of different profiles. First, we have for the rock embedment, which is the partial column frequencies. Then we have the full embedment that includes the rock and the soil above and just of the soil. We need these frequencies in order to understand better the transfer function results and the results of the SSR analysis. Next slide, we show the input motion, acceleration response spectra. This is now we're talking about reactor building. These input motions, as you know, they were enhanced to meet the NRC check, especially in the vertical direction. I want to point out the red line in the left, in the plot in the bottom, around, let's say, between 7 to 12 Hertz. There's quite a bit of energy added to the design response spectra, so you can meet the requirements for NRC check. The next slide shows transfer function results that we have obtained, and this is for reactor building. Basically, I mean, as you can see, we have a large peaks of the transfer functions where we have close to the soil column frequencies, especially for the partial integrated model. They are right where the rock embedment frequency is. Now, when we come to the structural frequencies, which are the first peaks of the transfer functions, then if you can go compare them for the two soil cases, then you can see there's not much of difference. They're almost the same, which indicates like for the structural frequencies, the responses are not really affected by the subgrade variation of subgrade properties. And this makes sense because this is a large building. It is relatively shallowly embedded. So now when we compare these, the results from fully embedded models and partially embedded models, that we can notice that for the structural frequencies, or the ones which basically govern most of the response of the building, there's not much of difference. They're pretty much the same. So based on this perspective of the transfer function results, we can conclude that addition of the soil on the top of the rock really doesn't change, doesn't result in any shift of frequencies, or doesn't really affect it has a very minor small effect on the response. Now the next slide shows comparison of structural response spectra. Basically, when we compare here, we compare the results from the two cases, lower bound and upper bound, with partial and full embedment, so you can see how they are, and also we compare them with the DCD spectra, and we compare it with what we have in the left side of the site-specific design spectra. So now the comparison of the structural response spectra shows that, from transfer function results, there's no shift of frequencies. Where we used to have peaks in the results from the partial embedment, they are in the same place where the full embedment. The only difference is here is that for the vertical motion, and especially in this particular location, because of the NEI check, we added up to 70% more energy, the peak went up quite a bit. So you can see exceedance there of 30% or so. So overall, in terms of vector building, response is where it is, but because of the NEI check, basically we have experiences in the vertical direction. Now we go with the control building, which is much smaller building, and it's deeply embedded. Actually, half of it is underground. And this shows the model. The modeling is similar. I mean, we use the same approach. The soil, the profiles of the site model represent in situ, which are string compatible. And then engineered fill and concrete fill is part of the structural model, and it's more as a solid element. So we have solid elements for the deck fill at the top, and then we have solid elements for the concrete around and below the foundation of the concrete building. So basically the model is also refined enough to pass frequency up to 54 hertz upper bound field case. Now if you go to the next slide. Okay.
Question, sorry to interrupt. This is for the control building, and the passing frequency for the upper bound is 64 hertz. The passing frequency for the lower bound is 24 hertz.
Based on 20%.
Based on the, 1/5 of the show is like.
Right, and what we use is 50% higher of that for the...
That's the cutoff frequency.
The cutoff frequency?
No, that's the passing frequency.
Oh, passing frequency?
Yeah, this is passing. And
What you're talking about, what is 2 times or something?
No, 50% higher of the standard, of the criteria. So basically the cutoff frequency we run up to, what will be 36 hertz.
What's the actual number for the reactor building? Because I don't remember seeing it.
I didn't include that. That is similar. Yes.
Okay.
So now these are the profiles of the embedment for the control building, and the same the shear column frequencies for the rock, the full embedment, and soil embedment. And as we go to the next slide, you can see how this. This is due to motion here. It is all NEI check. It was enhanced also in vertical direction. In horizontal, I think a little bit like upper 40% in the vertical direction. So next slide. And these are the transfer function results, two soil cases, lower bound and upper bound. And as you can see here, we have the same situation with the peaks reflecting the column frequencies. Now, when you go in the structural frequencies, we can see some shifts of frequencies now. When we add the backfill, basically, we add the steepness to the SSI system that shifted some of the frequencies in horizontal direction to higher frequencies. So,
actually,
yes, I mean, not just backfill, but when we put the soil on top of the rock, both in situ and backfill. So what we see is that we observe in the horizontal direction some effect of the additional stiffness due to the embedment.
Can I stop you there?
Sure.
So here I see the peak shifting a little bit to the right. Starting about these.
Right. So those are the structures.
Okay. So you see it here, but you don't see it in the reactor building.
Yes.
Is that your conclusion?
Correct. And
what's the physical explanation?
The physical explanation, this is a smoke. First, for the reactor building, the soil embedment is only it's like 30% addition. Because of the site configuration, for the control building, now the building is 50% more embedded. And then we are dealing with a building which is very light, I mean, it's much lighter, and it's more than half, I mean, almost half below the ground. Reactor building is a tall, big structure, and I think the embedment ratio is like maybe 20-30% compared with here, where we have quite a bit of embedment. So, I mean, it really makes sense that for control building, the embedment will affect much more the response than for the reactor building.
The system is much stiffer than...
Right, of course. Right, it's a box.
Right.
Deeper in.
In soil, right.
Okay.
And then we have additional more soil than we used to have for the reactor building.
Okay.
So now these are the structure response spectra. The consequence of this frequency shift is illustrated in this slide for response in y direction. So you can see that the red peak basically what happened. Now the response went to the higher frequencies where the input motion has higher energy content, and we exceeded what we have calculated in the partial columns. Vertical, the DCD governs still the horizontal, we have exceeded this, which is around 30%. The next slide. So the preliminary results indicate that this actual response spectra at selected locations and for a range of frequency exceed the presented one in the FSAR for the reactor zone, fuel zone, and control zone. So based on this, I think it may be necessary, but we think it is necessary to revise the FSAR to supplement what we have right now in the FSAR from the partial embedded models with the SSI responses obtained from a fully embedded model. So basically, these fully embedded models will become part of the licensing basis. And everything else will be developed based on envelope of responses from the two models. And as we mentioned before, description in the FSAR will, what we have right now for SSI analysis of partially embedded models will stay in the FSAR. There's no difference in that. with some modification. And we will add description of embedded models and embedded models analysis in the EFSA. So basically, we supplement what we have so far. Now, the same question came. We realized that we are going to run for all three profiles. We ran for already for control building. We have the whole set of results. We're still doing some post-processing and looking at the results. But then reactor building, fuel building takes a little bit more time. So, but soon we will have results for that as well. And we will go incorporate everything in the standard design basis.
We have some basics for cracking frequency on the up to 24 hertz or something. Up to gigahertz.
We will have to compare with the motion as well. And basically, what we see as exceedances from the, as you saw before, it is in that range around 10-20 hertz happening. So, and we cover that range of frequencies. And if you can see the results also for, now I compare, for example, if you go back to slide number 55, and the upper bound is the one that pretty much got.
The upper bound analysis is with the higher,
yes,
higher results because it's the stiffer soil.
Stiffer, there is a less dissipation of energy in the submit.
And that one does have the 50
exactly
passing frequency.
Yes.
How about the pressure situation? Which one gives you?
Lateral pressure is up or down because it's
Pressure means the lateral pressure.
right.
The bound is still higher now?
I think so. Because for base estimate we still don't have results for that. As I said, it's ongoing work. I mean, it's and then we will get something else. I mean, the purpose of these results is just to give you a feeling what we understand. It's not.
So what I understand from this is also a governing case. So you have this case, that case, and then you have pre-solved the file. Then you probably have those 50% cracking, 0% cracking, 100% cracking of the diaphragm floor, another situation. I don't know what else. So it should be nice to have a tabular
Matrix.
matrix.
The analysis that we are going to do. Okay. Yeah.
The diaphragm floor.
These are the composite steel concrete elements.
Basically, want a table that will summarize all these
situations that you were covering.
A table in your sir.
Yeah, it's nice. Easier to see.
So we can go to slide number 62. Here, because we have results for also cases for control building, I just wanted to give you a feeling what will change in terms, and the most effective will be structural response spectrum. The red line is the one that will include the revised one that will include or enhanced that will include the embedded cell cases. And if you can see that, what difference between.
Which one is that on the right side?
The black curve is the DCD. The blue curve is what we have in the EFSA right now based on partial embedded models. And the red one is the granular partial.
It looks like structural response also has gone up.
For control building, yes, it did. Yes.
I mean, not just the spectra, the VPA.
Right.
That's control building as well.
5% damping, I assume, right?
Right, these are all 5%. So, I mean, this is for this study. I don't know if you have any other questions, but I think we have a pretty good understanding why we have the experiences, and we have good understanding that we have experiences.
Because not only, what we narrow focus, like in Fermi we have seen a little different. This is
Oh, but Fermi was a different case.
Now we understand, yeah, it's a different situation.
Fermi for the motion that
They use the same motion.
exactly.
And that's a big difference in your case.
One and the second thing is they have a lot of margin there from the decision to come.
No experience, right? From no experience.
No.
Not on this situation, because they have same is, no, no experience.
So the next study I want to present to you is, as we spoke about the sliding stability evaluation, there are two issues that we have RAIs. One is regarding the average window, and the other one is the use of sliding coefficient. So basically, we did alternative evaluations with the objective to demonstrate that what we have right now in the XR as sliding stability evaluation, the other steps. As I mentioned before, the sliding evaluation right now is done for the building for the most critical fault case. And that is most critical because that's really the largest magnitude of required level of passive resistant pressure. Now, the methodology we are applying differs from what is in the BCD. So it's a different methodology. And basically relies on it takes directly the SASI result of reaction forces at different interfaces, SSI interfaces. So we look separately what are the forces on the basement itself, what are the forces on each wall, and what are the forces on each side of the basement. So now, what is the justification of using this kind of approach and why it's so different than the DCD? I mean, DCD is a generic approach that applies to also for all different ranges of soil conditions, which include soil and rock and everything. Now we have a quite different situation in this case. We have a building suffocated in the rock with a full concrete, and then we have some soil on the top. In this case, as you saw from the SASI results of displacement, the buildings, they don't experience much of displacement. So what is happening is we have experiences of the shear resistance at certain surfaces. They are of short duration. So we can make the assumption that what linear analysis, in this case SASI, give us the distribution of these contact stresses can be used for the calculation. Now, of course, not to address the issue of using moving window averaging, we use time histories which do not apply the moving average window, so they are unfiltered. Also, we conservatively assume that the emphasis of time and the base shear resistance is exceeded, that we use dynamic coefficient for that resistance. Basically, after sliding occurs, although there are not enough deformations to it, we are lowering the value of friction coefficient that we use. So these alternative evaluations provide the magnitude of maximum lateral passive resistant pressure on the control building walls that are required to achieve the sliding stability for safety factor of 1.1. We still apply the same. Whenever at the base we don't satisfy the safety factor of 1.1, then we calculate how much passive pressure we will need to meet that safety factor. So we can go to the next slide. Here, I will try shortly to describe the methodology step by step. Basically, the first step is to calculate the contact spring forces for all 9 surfaces. Basically, we're calculating 1 at the base, then we calculate for each basement size, and we calculate 4 contact forces at the 4 walls.
When you, the contact forces on the exterior walls, they go up to what height? Is it just top of the wall? Or is it?
Yeah, because we are dealing now with the spatial embedded wall.
Okay, so it's just top of the wall.
Right.
So how many surfaces is there? Four?
There's 4 for the walls, then 4 is for the sides of the basement, and 1 at the bottom, so it becomes to 9. Now the second step, we calculate the effective weight of the building, and we calculate the vertical reaction at the base. So the difference between what we have in the XR and now, we are taking the base reaction, and those are just the reactions at the base of the control building, and we take out we add the static portion into it. So after that, we calculate safety factors. This is same that we do for in the XR. We use coefficient of friction of 0.6, and we calculate safety factors for sliding in X and Y direction. Now, in instances of time, when the safety factors is less than 1.1 as required by the SRP, we are calculating so-called leftover force. Basically, the force that is not resistant at the base and it has to be transmitted to the wall using dynamic friction coefficient of 0.5.
I'm sorry, I have a question between steps 3 and 4. So step 3, V to capital B is the vertical reaction, essentially the gravity minus seismic couplers.
Yes, VB is gravity minus and plus minus.
Plus minus side.
But the absolute minus.
Okay, so it's okay, so that's net downward force.
Right.
So you call it B. I get confused because I think of that shear, but it's okay. So that's the net downward force times the coefficient of friction divided by R sub B, which is the base shear. All right?
Yes.
Okay. All right. So whenever that's exceeded, it means you need something more than just shear at the base to resist that.
Exactly, which is the same approach that we have been using.
Okay, so you're computing that at every instant?
Yes.
Okay.
It's in tandem.
Okay.
And then every instant, when safety factor is less than 1.1, first you calculate that leftover force in the base. Basically, that is the force in the shear force in the base that is not resisted by the shear resistance. So basically, that force has to go somewhere else. It's transmitted to the wall to resist it. I don't know if you can go to the other slide.
Ready?
Yeah.
So besides this base leftover force, we also there's no resistance in the wall. We recognize that because we can use waterproof membrane. So we also take leftover force from the sides of the wall because there's no shear resistance to resist. Or it's very small, so basically assume that the waterproof membrane cannot transfer any shear, any friction. So, depending on the orientation of the forces, either we add that force to the overall leftover force, which is I don't know what I use there for that. But if those forces are in opposite direction, then we can subtract it from it. So now, depending